My friends, we're going to solve a real exam problem in thermodynamics in general chemistry, and it's one that asks if the system gains or loses energy as work. And this is not a hard exam problem, but it's something you need to know before we go a little bit deeper. So this is it. So assume that the reactions occurred under constant pressure, 1.0 bar, and temperature 298 Kelvin. Did the system gain or lose energy as work? So we don't care how much work it gained or lost, just if it was positive or negative. And we'll start off with our equation for work, for pressure volume work equals negative P delta V. And I derived this in the previous video. If you want to know where it came from, you can go check that out. And the change in volume, we're going to assume that the change in volume for a gas is much, much greater than the change in volume for a solid or a liquid. Okay, the change in volume for a gas, I think that's reasonable. These are much more compressible than solids and liquids. And a gas doesn't say anything else, so we're going to assume that this is a ideal gas or a perfect gas that obeys the ideal gas equation. Now, if we look at the change in the reaction here, pressure is constant, right? Constant pressure. There is a change in volume, and that change is due to the change in the moles of gas. So delta N of our gas. R is a constant, and T is constant as well, constant temperature here. Okay, so if we plug this in, and we're not going to plug in any numbers, but I just wanted to plug this in just so you see it. So negative P. Now this delta V, this is, let's see, delta V. I'm going to solve for delta V just down here. Delta N gas, RT divided by P. And we're going to substitute this into here. Okay, so delta P is delta N of the gas, RT over P. Pressure cancels out. I explained that in the previous video why, but it cancels out because we've already considered the change in moles and the temperature, so we don't need the pressure here. And okay, so we're at negative delta N of the gas, RT. Now, we know what T is, we know what R is, but what about this change in moles? What happens to it? Well, the change in moles of the gas we get from the balanced equation here. I'm going to give ourselves a little bit more room. Change in moles. Change means the final minus the initial. And based on the balanced equation, afterwards, finally, that's like the reactants. This is final is the reactants. And not the reactants. Oh boy. Products. Final means the products. We're going to products. Terry, come on. We're going to products. So there's no gas afterwards. So that's 0. And initially, based on the balanced equation, there's just a 1 here. So that's 1. So the change in moles is negative 1. So this whole thing becomes, I'll write it down here just so it doesn't get too messy, equals negative, this is negative 1, RT. And we can cancel these negatives out. Negative times negative is positive, which makes it RT. Okay, so the work is equal to RT. Now, this RT just means per mole of the reaction here. R is a gas constant, that's positive. Temperature is always positive because it's measured in Kelvin. So this is always going to be greater than 0. That means work is greater than 0. That means the system gained energy because work is positive. So it gained energy as work. So what that means is if it gained energy, that means the surroundings did work on the system. So if this is our gas, to do work on the system, you got to push down, right? It's an opposing force. You got to push down. You got to compress a piston so the volume gets smaller. And we put energy as work into the system. So work is positive because the system gained energy as work. And that makes sense because it compressed. And it makes sense that it compressed because we had a gas. We no longer have a gas. So that gas compressed. Well, it didn't compress, but it actually reacted to go down into a solid, so a smaller volume. Okay, these next two examples are very similar but slightly different, so make sure to watch through because there are some subtleties in there. We'll start off with our equation. The work is negative delta N RT because we care about the change in moles. And this is equal to the moles of the products minus moles of the reactants And it's not actually the moles, it's the stoichiometric numbers in the balanced equation. But I like to say moles to keep it simple. Hopefully that's not confusing. Now, in the products, we have one here and one here. So there's two total. Two, oops, two minus, and the reactants have two as well. There's two. We count these, we just add up all these coefficients. So there's two. RT, so that equals 0. So the work is 0. Big fat 0. So what that means is that there is no expansion or compression of the system here due to this chemical reaction here. No work is done. All right, so the next one here, work equals negative delta N RT and negative. So some of the products, not the reactants, some of the products would be 3, because we add these up, make sure they're all in the gas phase. Only add the ones that are gases. We don't include liquids or solids. Minus the reactants, so 2 RT, and that is equal to negative RT. So the work is negative. Work is less than 0. And when it's less than 0, that means it lost energy. The system, the reaction lost energy. So if we have a piston like this and we have our gas in here around like this, it loses energy by performing work. It does work. And when the system does work by expanding, it loses energy. Now, it's an expansion due to this chemical reaction here because we're creating more moles of gas. Because we're creating more moles of gas, imagine that's pushing on a piston just per se. It could be a balloon or anything, but it's expanding the volume. The change in volume is getting larger. And because of that, the system is losing energy as work. So work is going to be negative in this case. Okay, so these are real exam problems. They are simple exam problems. And if you want to see more challenging ones that could come up on your midterms or final exams, then check out my next video and all the other videos in this series where I just go to give you an onslaught of exam problems so that after watching these, working through problems, you should feel like you're awesome at thermodynamics. That's the whole goal. I hope you enjoyed it. Thanks again. And yeah, see you in the next video. Cheers.